Welcome everybody to the first 2022 From Discovery Science to Industrial Applications series talk, which today we're going to be learning from Professor Ruchi Choudhary. This series of events started 5 years ago. We organized it with Louise from the beginning. Louise and I have developed this, I think, successful relationship, who is on the call, with Cambridge Network. And we take this view that sometimes there is some research, some ideas that are ready, mature, to be taken out there for the rest of the world to see coming out of our academic little bubble and explaining and sharing with the outside world. And that's what this series is about. We do these talks once a term normally, but COVID, which was an interesting situation, as we all know. And I would leave it to Aga to introduce the speaker.
Good afternoon, everybody. My name is Aga Iwasiewicz-Warnik. If you have not met me before, I'm Director of Partnership Development at the Maxwell Center. So the talk is in partnership between us at the Maxwell Center and at the Cambridge Network, as Monica explained. And it is my pleasure to provide an academic perspective introduction today to Professor Ruchi Choudhary, who is a professor of architectural engineering here at the Department of Engineering in Cambridge. She sits within the Civil Engineering Academic Division, and her specialty is in building simulation and environmental characteristic of the built environment, also at the urban planning level. She wears many hats in Cambridge. She is involved in the Cambridge initiative called Cambridge Zero, which is the university-wide initiative. She is leading the most multidisciplinary energy efficient cities initiative, which is, I think, we will be hearing more about today. She also chairs a special interest group, technology special interest group on built environment, which brings together academic perspectives again with industrial guests in a the Chatham House format for discussions twice a term. So I think there's plenty of opportunities for us to follow up, but without further ado, I'll hand over to Ruchi to take us through her presentation now. Thanks very much.
Thank you. Thank you very much, Aga, Louise, and Monica, for arranging this. Very pleased to be here. So yes, at Cambridge, I've been running a multidisciplinary group called the Energy Efficient Cities Initiative, and our projects span from city scale, looking both at underground climate change with respect to anthropogenic heat sources, heat sinks, efficiency of geothermal systems, right to the heterogeneity that should be part of energy planning in cities, and also sort of building scale retrofit models for energy efficiency. But today I'm going to be presenting a rather unusual project that has kept us busy, and that's basically on it's urban agriculture, but it's really about building digital twins of built environments, and this is the lens through which I'll speak about it today. So the project, well, it's a digital twin of an underground farm. It's the first underground farm in the world. It's in London, below Clapham, and they grow microgreens. So a quick sort of recap on why I got interested in this in the first place. So plants, as we know, transpire, and in the process, they have a net impact of cooling the environment, of course, with the caveat that with an increase in moisture content of the air. Plants also photosynthesize, which basically affects net removal of CO2 and addition of O2 into the surrounding environment. So we kind of see these as synergistic benefits with the built environment in urban areas, because urban areas, as we know, generate a lot of waste heat and CO2, which is what plants primarily require to grow. And so in using the waste, we get net benefits back into the environment as long as we can design and control it efficiently. So, you know, we've been looking at typologies of urban agriculture around the world. We've seen intense plant factories in Japan, and then very small scale bespoke farms that have been sort of coming out of very small grassroots level across at Liverpool in the UK. We've come across rooftop farms across Europe, and of course this one, which is very uniquely underground in tunnels. And right from large scale to small scale to educational purposes to commercial farms. So we're looking at all across these typologies of, very sort of intense, high growth factories to extremely small scale where they are properly integrated with the urban environment in terms of exchanging warm air that is rich in O2 from the rooftop greenhouse onto the office environment and recycling the air back into the space. Now, once we got interested in it, of course, as I said, you have to be able to design and control these efficiently. Otherwise, you end up with a lot of moisture in the air and extra problems. So we started by asking that, can we really quantify these effects? So we take some standard operating environments in which plants grow and by which we occupy buildings. So, regular office level lights, temperatures, relative humidity, at standard rates, a standard sort of assumption about plant growth in such areas, and the characteristics of the plants themselves in terms of, how the leaf exchange heat and mass transfer with the environment. Given that we kind of have a rough estimate of what these effects are in terms of heat loss by the plants and heat gain attributed by the presence of humans in a space, big difference in the moisture contribution, and of course the CO2 absorbed by the photosynthesis as against the CO2 input by human beings. Now, we recognize that we can't really quantify these effects. It would be more accurate to say that we can approximate them. And the approximation really comes from a lot of sort of complex ways in which plants exchange energy with the surrounding environment. And that actually, it's a bit challenging to do it accurately because models of heat and mass exchange between the environment and the plants are largely empirical and limited to specific crops. Plus, we are interested in urban integrated agriculture, so integration with existing infrastructure or with existing buildings. And we don't really have exact models that can accurately determine that this is the amount of waste heat and this is the amount of waste CO2, and that, that goes into the plants and that gets exchanged, sort of with the building. And then because these operate as almost factory-like environments, monitoring, as I will show you, can be very difficult because these are, wet environments, very active and often bespoke, especially in the context of urban integrated agriculture, which happens in very bespoke special sites, as you will see in this example. So despite all the hype, I see digital twin as a useful concept to explain what we are trying to do here, which is that we have a physical entity, which is this urban farm that we are trying to understand, and we are trying to make it more productive in terms of how they grow crops, but also more energy efficient. And we have a simulation model that is a virtual representation and a physics-based representation of the actual farm. But we know that the representation is inexact, but we still find it useful in order to understand the complex relationships between the environment and the plant. Now, the data, by monitoring the urban farm, we continuously learn more about what's happening in the farm, and we are accordingly able to nudge and improve our model to be better reflections of reality. And that's exactly what the concept behind digital twin is, that you have a physical entity, you have a virtual model that's based on your understanding of the process, and you use data as a medium to enhance both and hence benefit the final physical environment in terms of being able to understand what's going on there and being able to forecast or predict. So basically, that's what we are attempting to do here, that we take the farm from a snapshot and develop it into a dynamic digital twin that has data connected to its simulation counterpart, and there's feedback loops between the data and the model and the farm. So in terms of the platform that we are developing, we call it CROP. It's a cloud-based application which utilizes the flexibility, the customizability, and the evolution that cloud-native systems offer. And basically, it's hosting all the infrastructure, all the data infrastructure, all the modeling infrastructure, and all the back and forth communication between what's happening in the farm and what we are trying to do with respect to monitoring and modeling to better understand the processes in the farm. This is, as I said, these are tunnels 30 meters below ground, below Clapham Station. These were air raid shelters, and basically since 2015, they've been operating as commercial farms. There's propagation area, growing area, etc. And we have been, since they started, we have been experimenting with the appropriate sensor networks to try and capture the environment inside the farm, but also the processes in terms of what's happening on a day-to-day basis. And that's, I can tell you, that's not been very simple. It's not so straightforward to monitor things 30 meters below ground. There's sort of rudimentary issues like sensors falling apart, batteries not working, wireless systems falling apart, but also the fact that this is a functioning environment. Ultimately the farmers want to get on and do things their way, and if they see sensors that are in their way, things can get moved, etc. So it's been a journey, and by now we have sort of 4 series of sensors installed in there. A lot of work and labor went into it, labor of love, ultimately ending in approximately 89 monitored variables across 8 loggers, 2 APIs, and enhanced with some manual data collection that, as we speak, we are now trying to also automate. The framework through which the digital twin operates is that, yes, you have all sorts of, the specific sensor data coming from the farm, the external environments, and, for example, the weather, the energy, in addition to manual records. That goes into a processing system, which involves a lot of sort of data curation, which is data cleaning, historic data interpretation, etc. And then ultimately, that has to be all translated into what is most important, which is what do you do with that information? How do you translate that into something that can be made sense of and can help the farm operate better? So there are 2 types of models that I'm going to talk about now that we've been working on with this data. So basically the challenge here is that you have all this information, you want to translate that into meaningful information. So one type of models that we are that we have been designing are purely data models, which is basically using historical data to forecast the environment in the tunnels. And this is not so straightforward because we have to deal continuously. It's okay when you're building these with curated data, but when you want to build these with real-time data, like update every day, then it becomes challenging because you have to forecast even with missing data. You want to be able to understand spatial variations across the farm because some, I'll show you in a minute why that's important. You want to optimize the location of the crops and, of course, end up with operational improvements. So for example, the crop performance is very much dependent on temperature. So it works very well within a range of temperature. But the interesting part is that the variety of crops that are grown across this farm, not all crops do well in the same range of temperature. So that's where the historical data becomes very important, because otherwise we have no way of knowing which crops systematically grow better in a certain temperature range. So we try to keep a record of that. We try to keep a record of how, and the crop performance we quantify based on the number of days it takes for the crops to grow. It's approximately 5 to 7 days. These are microgreens, but also in terms of the amount that's ultimately harvested. So So we look at different temperature ranges, and then that again has an implication on where to grow the crops, because there are temperature variations along the tunnels depending on how close you are to the ventilation shafts, but also there's some vertical stratification. So we basically, for example, this is the top plot here. I don't know if you can see my mouse hovering, but the top plot here is the 2017 growth of crops, and as against 2018. And at the end of the 2017, we told them to grow a couple of their crops, for example, like the mustard and specifically the mustard towards the end of the tunnel, because the temperatures were sort of warmer there and they prefer that environment. And they immediately saw increased yields in these two crops once they moved them towards the back of the tunnel. Ultimately, I'm talking about temperature, but ultimately what affects these crops is temperature, which is that, it cannot be too hot or too cold. It has to be within a certain range. They also grow better at lower humidity, and I think that was one of the first things we discovered. And by the second year, they did install dehumidifiers within the tunnels, because there was no other way, because the ventilation rate is limited to where the current shafts are, this being underground. And of course, there's an effect of the light, but all of these also affect each other. For example, lights inside the tunnel, which is the main medium by which plants photosynthesize, also impact the temperatures in the tunnel. But the way they impact the temperatures in the tunnel is different, and that has a confounding effect with the external temperature. So that's also something that if we wanted to forecast the internal temperature of the tunnel, we cannot use the lights alone, because the external temperature also makes a difference in the decay, the temperature decay once the lights go off, or the temperature rise, the rate of rise once the lights come on. So using these, the external temperature and operational controls, which is basically fans, lights, and as basically lights, we use the energy used for the lights as a proxy. Using the operational controls and the external temperature, so basically we try to forecast temperatures for the day ahead for them. So just to give you some examples on, that of course we are not always accurate, but we are able to detect where the inaccuracies come from, and thereby we can continuously keep improving our models and their predictive accuracy. So for example, here, there is a bias of about 5 degrees, but we are able to see that the lights were off for longer. Somebody forgot to turn on the lights. It's as simple as that. And then that means it's going to affect the harvest over the next week or so. Then, in a sense, if on the days when operational conditions go as planned, we are able to predict quite well in terms of how plants are going to grow, and also accordingly at different temperature ranges. So if the temperature variation across the day is not much, or it's more, we are able to accordingly adapt the model. Ultimately, what we want to do with that is we want to be able to forecast. So we want to give some clear signals to the farmers how things are going to be over the next 24 to 48 hours in the farm. And we are able to do that with the quantification of the uncertainties or the ranges. This way we are able to capture the range. So even if we put our predictions against specific sensors, we are able to kind of follow the range, but at the same time also continue to learn and adapt our models as we go forward. Now, the second type of models that we've been working on are purely physics-based models, and these basically serve a slightly different purpose. They are for scenario evaluations. The farm, it's continuously growing. Like, for example, last week I heard that they're now going to start experimenting with mushrooms. So we have to continuously keep adapting and be ready to be able to help them expand efficiently, where they are going to need extra fans, where they are going to sort of benefit from heated areas of the tunnel, or areas that have higher moisture content than the others. So in those cases, actually, we do need some physics to be able to sort of nudge the predictions in the right direction. So these are 1D models, because this is a tunnel, and we have been working with plant scientists to improve the representation of photosynthesis within the modeling, and to take into account the fact that these are microgreens. And one example where the physics-based model became quite useful was when initially the farmers were debating when to put the lights on and off. So when should the plants photosynthesize in the farm? And that can be controlled, right? In a sort of in farms that grow with crops that grow with daylight, that you follow the sort of regular cycle. But here we did see that how much the farm gets overheated if the lights were on during daytime versus during nighttime, and basically we help them figure out that actually it's a certain proportion of the nighttime where it's better for them to photosynthesize, or to have the daylight in the farm, or the light, so to say. Now, so I've shown you the benefits of this physics-based model and what kind of things that we find it useful for, but it does break apart, in the sense that our predictions do not match the observations. And this is where, again, I refer back to the concept of digital twins, that if we have data, we can keep nudging our models to be better reflective of reality. So we calibrate our physics-based model. We use a Bayesian sequential calibration framework. And the way we've set it up is that normally in the past, when we've, for other applications, when we've calibrated physics-based model, we do that against a range of scenarios, and we are able to infer certain parameters that we then use to propagate the uncertainties to whatever quantity of interest you have, be it energy or be it maintaining certain temperature conditions inside buildings. But in this case, the parameters fluctuate, and also the environment that's that is sustained when the plants are growing is different from when the lights are off and the plants are not photosynthesizing. So we had to come up with a system by which we can continuously calibrate based on real-time data, and accordingly infer dynamically the changing parameters inside the tunnel. And so we take different periods of monitored data and accordingly infer quantities that we cannot directly measure. So, for example, internal air speed or internal ventilation rate, that's something that changes dynamically throughout the day, depending on how many fans are on, whether the doors are open, whether the shaft is open, and accordingly, we keep nudging our model to sort of identify where the ventilation rate lies in a certain period. And the reason why it's important is because both of these affect the farm environment in different ways. The internal air speed affects evaporation and hence transpiration, whereas the ventilation rate affects bulk air exchange. So they have slightly different effects on how plants grow. And so we use the monitored relative humidity data along with our physics-based model of the farm, and we use the particle filter to track both the internal air speed and the ventilation rate. And so by calibrating the model with the relative humidity data, which incorporates both the temperature and the humidity in the farm, we're able to nudge the predictions to match the reality better. And so then we are able to match the observations much better, along with the range of uncertainties. And then we use that calibrated model to see if increasing either the fan speed or the ventilation rate of the tunnel, we would be able to bring the temperatures back within the range that pleases the plants. So basically, it can also be used for scenario evaluations of actions, like what action would be most suitable or most effective to bring temperature back into the range that's required. So yeah, so in some instance, so the key thing becomes that what do you do with all of this? So with all of this, we have to translate it back into some simple things that the farm operators can interpret. And that becomes actually very, very important, both to sustain, it's important to sustain the digital twin, because unless we get good quality data, the digital twin will fall apart. And that requires buy-in from the consumers of the digital twin, which is the farm operators. So we have to keep them engaged all the time, so that, because we are not in the farm 24/7, we basically expect somebody to take care of the hardware that's giving us all the good information. And that can only be achieved by making them value what is going on there. And that has been a very important part of the process here, where we've engaged with the farmers initially by sending them manual reports every week, when we didn't have that, when we were just setting up the infrastructure and the communication. We would send them a report every Friday, and we would accordingly interpret simple actions that they should take on, certain ranges of external temperature, that which would translate into put another fan or increase your ventilation rate. So, for example, that also, we couldn't say that, okay, now you need 4.5 air changes per hour. They wouldn't know what to do with that information. So we used to translate that into knowing that the way that they change the ventilation rate is through this dial. So we would tell them, turn the setting towards 3 o'clock. So basically, the point being made is that, sure, what we do in research has to be useful, if it's direct, if that's the purpose. In this case, it was. But in order for it to be useful, there's certain steps that we had to take here. That, by now they are so engaged with the quality of the data and the data curation that if something goes off, they're the ones who alert us immediately. They kind of, and in fact, they've now invested in their own set of sensors as well, which they've hooked onto our digital twin, so that, as they're expanding, they are now investing into the monitoring infrastructure, because they realize the value it brings to their yield. And as we speak, we are continuously improving it. So we in the first iteration of this crop, we did have a kind of simple visualization, dashboard, etc. And by now, we are just about to release the second version of it, which includes the forecasting and the scenario evaluation of so the modeling itself. But there's still many challenges that we continue to face, which is that, 3D visualizations, there's always a cost benefit, because, they're difficult to load. So they're good to see, but they don't always, it's not always the best way by which you communicate useful outputs to a sort of fully operating environment. We have data coming in from different systems, different platforms, which we need to make sure that all of these are synchronized and used as cross-reference where possible. Deployment of physics-based models can be particularly challenging in these kind of environments, and especially from the perspective of reproducibility, that you always, in the sense that, are your models reproducible with sort of real-time data, and there the code robustness is an issue. Missing data is a big issue. No matter how well you monitor, you're always going to have data missingness, and that's something that we've been looking into quite a bit, how to tackle it. And so I end with some ongoing challenges, and we continue to work on it. We continue to keep adding stuff we still don't know, and so I'm happy to take questions from here. Thanks very much.
Thank you very much, Ruchi. Is there anybody that has a pressing question immediately?
No questions. I have a question. Can I? Oh, it's Louise. I'll turn my camera on if I can find the button. There it is. How energy efficient is it? Is that one of the things, one of the sort of rationales for growing underground, or is it literally to use the space to broaden your offering of crops? Say, if you're an urban farmer. I was just wondering about the energy efficiency of the lights, etc.
Yes. So yes, the big cost is the lights indeed. So because they're using the lights, but the lights also provide a source of heat. So they kind of double dip. And actually, when we took some plant scientists they were actually, their feedback was that this makes perfect sense, because the advantage is that the surrounding temperature is stable. You see, so if it was a rooftop greenhouse, you would have the added advantage of the daylight, but you would have much greater temperature fluctuation. So you would need, so LED lights actually don't produce that much heat, but the amount of heat they produce is sufficient to grow the crops well. So we haven't needed to put any additional heating at all because of the stable 14 degrees, 13 degrees temperatures around in the surrounding soil, and with the lights on. So that gives a big benefit. The second benefit is that the environment is very intense. So you grow a lot more per square meter than if you were growing with daylight, because you're stacking them in shelves, right? So it's a very, so per square meter you grow a lot more. And then the third, that your consumers are right where you are.
Yeah, I was going to say, actually, your consumers are probably just outside your door. They're not,
Exactly.
miles away. Yeah, exactly.
Exactly.
Ah,
So that way, the efficiency of growing really creates this balance, where otherwise you would say that, oh, you're not growing with natural light.
But actually, lots of growers grow with grow lights, even in polytunnels.
Yes, exactly. And then the thing is that rooftops could also be very efficient if, for example, there you have the advantage of daylight, but you get, especially if you end up using the waste heat from buildings.
Yes, from air conditioning. Yeah.
Exactly. So, things, we can think of so many environments that generate waste heat, like supermarkets, schools, hospitals. These are all CO2 rich environment and waste heat environments. And they also have I think these are also buildings that would directly benefit from having some food growing
Yes,
on their rooftops. So yes, so the tunnels ended up being a kind of good environment for these microgreens. They tried to do big leafy plants for a bit, but that wasn't as successful for some reason. But the microgreens have been a huge success, and also because of there's a very short time period, 7 days to harvesting, so it ends up being quite intense and productive.
Yeah, fascinating. And mushrooms as well, as you said.
Yeah, that I haven't seen yet. I'm looking forward to seeing that.
We have a question from Fiona. Have you explored any other scenarios where digital twins could be used in agriculture? Due to the huge variability in outdoor farming, I assume having a digital twin would be too challenging?
Well, everybody talks about digital twins, but they are challenging. They're quite challenging to deliver and to produce. So it's something that can be talked about, but the actual delivery of it as a product that can operate, it's hugely challenging. And I haven't seen any good examples of it, especially with respect to incorporating models that are able to give feedback. So the fact that it's challenging doesn't mean we have the technology to do it. We just have to understand that there is a we just have to bring it to the point where they start delivering something useful. and that's always a cycle, with technologies, that there's a cycle by which, you start to acknowledge what they are good for, what they are not so good for, and you tailor them to be beneficial. So, in the sense that even in this particular example, when we built it, we started with the visualization. But the visualization is actually of the tunnels, and you could go into the environment 3D, you could fly through, you could look at sensor health, etc. Those were all very good for fancy show and tell, but that's not what was needed by the farmers. What they needed instead was basically some very clear feedback on how to run the farm, so that they could see benefits in terms of productivity, see benefits in terms of energy efficiency. And I think the controlled agriculture environment is actually very good venue for these, because actually a lot of them now also rely on automation, especially when they are, sort of very large and intense. So that's another place where digital twins can be very beneficial, because they can guide and nudge what you're trying to automate with respect to data as it comes in.
Haga, you had your hand raised.
Yes, thank you, Ruchi, for an amazing talk. I was just wondering, so the way you described it, I'm not sure if I got it right, but at the moment, the farmers you work with pretty much do all of the heavy lifting manually, do they not? So you provide them with feedback, well, meaning like turn the knob to the 3 o'clock and so on. So I was just wondering, because of course clearly there is a future prospect for this sort of probably on average smaller scale agriculture to really make it to urban environments, and I have a feeling that probably there it would really benefit from also automated processes for the agriculture that can be informed by the data coming through the digital twin. And I wonder if it would be, or you're probably thinking about it already, is it possible to take the insight and the data that your models produce and make it ready for a machine to take action based on it? It's probably easier than human, but maybe I'm wrong.
No, it's possible. It's possible as long as you tailor it to the environment. So already we are looking into that for the tunnels. So that's the next iteration of work. And they are becoming increasingly interested in it, because initially they had about 700 square meters of grow area. Now they are getting to the point where more and more they see the value of automation and some automation of the processes. So we've already, in fact, right now we have a small project where we are automating the registration of the yields. So we are looking into computer vision, we are looking into ways in which we would, because right now it's very labor intensive, the way they log the yield and the way they've been doing it for us, actually a lot of it, they do it for their business purposes, but for us, they've also been sort of logging what grows where. And so we are automating that. Then we are already looking into other processes that could be automated. There's a new PhD student from AgriForward CDT, who's very interested in automation, and he's going to be looking at exactly this issue. But we are also quite keen to see how what we have learned in terms of the digital twin development for this underground farm can be applied to other areas. So we are kind of forming a community of UK growers who are interested in using the urban landscape and the derelict spaces, urban infrastructure. So we are growing a community of those, and we are saying we are willing to work with you to kind of, transfer and tailor our models and digital twin technology so that it can become something that can be used more widely, especially with respect to controlling the combination of ventilation, airspeed, humidity, temperatures, humidity automatically.
Do you have any partnerships with industries?
So growing underground, we have a very strong and staunch partnership with Growing Underground by now. We also collaborate with plant scientists in the Netherlands. We have been looking into other companies that do aquaponics. So yeah, it's something that we have been talking to a few other companies who are interested in this in the Midlands. So yeah, right now it's a niche community, but it's growing. It's no pun intended.
You have another question, Aga?
Yes, basically, beginning of it was asked by Louise, and my second question is, how much capacity do you have for further partnerships? Because I can see quite a few emerging connections with some of our existing partners in the Maxwell, but also other people who are looking at this area. And the question is there anything in particular that a specific partnership coming in to join forces with you would bring value at the moment?
Yes, so of course we are most interested in working directly with farmers. So in the sense, because it's fascinating, we learn a lot, we can help them, and so right now we've been focusing on developing this community of urban farmers, people who are starting up, like in underground farm. When I went and met them, they were basically experimenting on a 25 square meter table, and but to do so, we also have to widen our team, in the sense that we are interested in energy and environment, but farmers are interested in so many other things. They also, because these are hydroponics, they are interested in understanding how to optimize the nutrients and how to also tailor the nutrients so that the plants can also potentially serve medicinal purposes, the microgreens. Or, from the perspective of automation and control, there's so much more that could be brought in by experts in cyber physical systems. So we have formed a kind of academic group as well that's wider than ECI, that incorporates researchers from across the UK, representing these different specialisms and expertise, so that we can also reach out to the wider community of people developing cyber physical systems, people who want to experiment with what kind of crops can grow better with hydroponics. So that's another thing that's on the agenda. And I also there's also an interest from designers, architects, etc. I've also been approached by architecture firms, because if they want to understand how to incorporate greenhouses within their buildings, then that exchange, that symbiotic exchange, needs to be understood, and that's where that kind of audience also can be valuable to us.
There's also the possibility, I guess, to interact with the Centre for Novel Agriculture Products in the Northeast. They do a lot of research with genes and stuff in plants, but it could be a good idea.
Exactly. Yeah. So we are
towards food security, but also to decontaminate land and all sorts of other issues. So it could be an interesting thing to follow up as well.
Yeah, so we have that on the agenda. So we did put together a kind of plan, so to say, of how we want this to grow and what kind of sort of industry partnerships we want. And that's something, in the sense that's something that definitely we will be expanding beyond the remit of what me and my research team are able to do, both academically and in terms of, industry.
Fantastic.
Do we have any more questions from the floor? The virtual floor? Deafening silence today.
It's the online meeting fatigue, maybe.
It might be. But it was a fascinating subject. But it really is, and there must be. Sorry. There must be lots of other applications for this technology and this measurement and things. It just brought sort of memories back of going to Iceland and seeing all the geothermal kind of greenhouses and things there. You just think there must be huge applications for this sort of farming, and especially in new environments like new urban blocks of flats and stuff, where you've got maybe a car park and lots of air conditioning units expelling all the hot air down there and heat pumps and stuff. Yeah, there must be loads of applications for this. I think it's really exciting.
Yeah.
So if there's no more questions, then perhaps we shall bring
There is one.
There is one. We've got one.
Hello.
Hey, Manar.
Thank you for the really interesting presentation. It is a lot of online fatigue. I was really looking forward to this in person, but here we go. I have a sort of a bit of a left field question. Where does this stand with applicability for the International Space Station or potential space travel farming, basically extraterrestrial farming?
That is a left-sided question. Well, you know, I haven't thought of that. But it's an interesting point. But because given a set of environment, basically what we are trying to do is have soil-less farming, right? And be able to understand the interaction between the plant and the environment. So if we are given some constraints on how the environment is going to be, we could work out how, you know, plants would grow in there, if that answers your question.
So it seems that it could actually be a good one for, because I mean, with loading and reloading the International Space Station, obviously weight is the biggest constraint, and food with freshness of food and whatnot. So with all the sort of growing companies in private space travel, I wonder if that would be a good partner actually.
Yeah, I mean, yeah. So basically, this is, you know, things are easy to grow with hydroponics. You just have to understand the right environment, the right nutrients. So possibly.
Cool. Thank you.
Well, if there are no more questions, I think we might just close this call today. Thank you very much for attending. Thank you, Ruchi, for being our speaker today. Fantastic talk. And I think it leaves us with a lot of food for thought for future possible collaborations and partnerships and otherwise life thinking.
Yes, no, absolutely. I want to echo that. Thank you so much. That's really, really interesting. And I was looking at to see if Fiona was still here. Fiona works, she has disappeared, but she works for a sister network of ours called Agritech East. So I think she was very interested to hear your talk today. So thank you very much.
Thank you.
Thank you once again, Agla and Monica.
Bye.
Thank you.